All right, let's get right into this. Welcome back to The Explainer. I'm your master coach, and today we are executing the absolute ultimate Cambridge exam breakdown. We are looking directly at Cambridge AS and A-level mathematics, specifically syllabus 9709, and we are putting an intense, high-powered laser on one of the most notoriously polarizing topics on the entire paper. I'm talking about section 3.7, vectors, more specifically, the equation of a line r equals a plus lambda b. Now, if you've done past papers, you know this topic is going to show up. It appears in virtually every single examination series. It's completely unavoidable. But more importantly than that, it is an absolute goldmine for marks if you actually know how the examiner's grid works. Our high-stakes goal for this session is simple, but it is totally transformative. We are going to maximize your method marks. We aren't just going to talk about crunching numbers and finding the right answer. Anybody can plug numbers into a calculator. We're going to decode the literal architectural blueprint that the principal examiners use to grade your papers step by meticulous step.
So here's the core paradox I see every single year when I read through the global examiner reports. It always comes down to this one question. Why do students consistently forfeit marks in vectors when they actually know the formula? Think about it. You walk into the exam hall, your brain is packed with info. You know r equals a plus lambda b, you know exactly how to execute a dot product, and yet you get your paper back and you are missing critical marks. Why does that happen? Well, it happens because simply memorizing the mathematical formula is not enough anymore. The assessment framework for 3.7 vectors demands logical, highly structured reasoning over superficial breadth. If you just dump raw numbers onto the page hoping the examiner will figure out what you meant, without actually demonstrating the theoretical architecture behind your math, you are going to bleed marks, and we are going to stop that from happening today.
Here is our visual roadmap for the session. We've got 5 steps. 1. Foundation and objectives. 2. A strategy debate. 3. The structural matrix. 4. A pause and practice challenge. And 5. Our ultimate recap. Let's dive in.
Starting with Act 1, we are deconstructing the exact target questions you'll see on the paper.
Let's look closely at the theoretical core of the equation itself, r equals a plus lambda b. On the surface, sure, it's just algebra, right? But in the context of the Cambridge benchmarks, this is a theoretical architecture resting on incredibly precise definitions. The r is your general position vector. It's mapping out every single possible point in 3D space along that specific line. The a is your anchor, a specific known position vector getting you onto the line in the first place. The lambda is your scalar multiplier. It's the parameter that stretches or compresses your movement. And the b is your direction vector, which is the fundamental trajectory you're traveling on. But here's the secret weapon, and this comes directly from the principal examiner reports. Candidates who explicitly reference cross-topic connections achieve significantly higher marks. What does that actually mean for you? It means you have to understand how this simple line equation integrates with simultaneous equations, with coordinate geometry, and even with trigonometry when you're asked to find angles between 2 lines. It is all connected, guys, and your structured written reasoning needs to explicitly reflect those causal relationships on the page.
And this hierarchy brilliantly illustrates exactly how the marks are distributed. The assessment objectives, or AOs, for vectors target 3 completely distinct cognitive domains. Step 1 is knowledge and understanding. This is AO1. This is just knowing the vector equation or knowing how to set up a direction vector by subtracting the coordinates of 2 points. It is the foundation, absolutely, but it is definitely not where the big marks live. Step 2 is application. This is where you extract the data from the text block, set up your equations for 2 intersecting lines, and apply the correct mathematical format. But step 3, critical analysis and evaluation. This is the holy grail of the Cambridge mark scheme. This higher-order objective demands that you check your answers for reasonableness and that you compare different mathematical approaches. For instance, imagine a question asks you to show that 2 lines are skew. You have to critically analyze that whole system. You literally cannot just fail to find an intersection, throw your hands up, and stop. You have to evaluate the fact that their direction vectors are not parallel first, and subsequently prove that the simultaneous equations yield no valid, consistent solution for the parameters. That critical, explicitly written step of justification is exactly what unlocks the highest band of marks.
Let's see how this builds into the absolute most common pitfall I see: superficial breadth versus analytical depth. Let's decode the Cambridge command words here, because they are everything. If a question literally just says calculate, you can often get away with a straightforward, speedy computation. But if the command word is show that, or evaluate, or to what extent, the game changes entirely. Superficial breadth is what happens when a panicked student writes down every single vector formula they know, just crossing their fingers and hoping one of them hits the target. They find the dot product, they find the cross product, they write down the magnitudes, but they completely fail to link any of it to the actual scenario in the question. Analytical depth, which the assessment framework heavily prioritizes, is choosing the exact singular mathematical tool needed, applying it systematically, and explicitly proving why it works. If you misinterpret a command word like show that lines do not intersect, and you just write at the bottom of the page, lines are parallel, you are going to face an immediate marking penalty on the examiner's grid. You've skipped the analytical depth required to prove they aren't skew. You must follow the logical sequence.
Moving into Act 2. This is where we look at a real strategy debate between two completely different types of students. I want you to imagine we are stepping into a shared study suite right now with two incredibly dedicated scholars. We'll call them Alex and Sam. They are staring at the standardized procedural framework required by the examiners, which goes like this. Step 1, identify elements. Step 2, apply relevant principles. Step 3, execute analysis with clear, readable working. Step 4, verify your results. Step 5, present everything in the appropriate format. Now, Alex is an absolute machine with formulas. Alex argues that they should focus entirely on textbook data inputs for the early stages. Just smash out the dot product equation immediately, right away, to save precious exam time. Sam, on the other hand, is fighting to build a flexible analytical thesis. Sam wants to explicitly define the position vector of the foot of the perpendicular first, clearly communicating the logical flow to the examiner. Because Sam knows that this exact explicit communication is how you unlock the top-tier method marks at the very end of the timeline.
Let's actually look really closely at their debate, because I guarantee you've had this exact argument in your own head during a mock exam. Alex is literally tapping the past paper, saying, look man, we know the point is P, we know the line is L, the direction vector is B, let's just write down P minus L dot B equals 0 and just start solving it. The examiner knows what we are doing. We need to save our minutes for those brutal integration questions at the end of the paper. But Sam immediately stops him. Sam points at the laptop screen and says, no wait, look at the principal examiner reports right here. If you make a single tiny arithmetic mistake in that massive algebraic expansion, and you haven't explicitly stated your general vector R first, you lose every single follow-through method mark. Every single one. We have to build an argumentative thesis. Alex sighs and rolls his eyes. An argumentative thesis in a math exam? Are you kidding? Yes, Sam insists. We have to actually write out the words, let f be the foot of the perpendicular, position vector of f is exactly equal to the line equation a plus lambda b, then we write vector pf equals f minus p. We have to show the examiner the exact logical step we are taking before we calculate the dot product. We are interpreting the relationship, Alex, not just crunching numbers blindly. And so they go back and forth. Alex wants the speed of superficial breadth, Sam demands the absolute safety of analytical depth. So what do? They rewrite their opening lines live, shifting from a raw, unsupported, messy equation to a heavily structured, step-by-step breakdown that perfectly matches the data interpretation requirements of the mark scheme. This is the difference between a B grade and an A star.
Let's move to Act 3. We need a system upgrade to handle the roadblocks you're going to face.
Okay, strategy check. Before we unlock this ultimate problem-solving matrix and show you the top-end paragraph structure to help you crush your upcoming exam sessions, you need to make sure your revision feed is perfectly optimized. Take 1 second right now to subscribe to Ace the Exams at the handle @AceTheExams. Enable all notifications so you never miss our weekly Cambridge exam breakdowns, no matter if you're sitting for IGCSE, O-levels, or ASNA levels. All right, let's step back into the study suite with Alex and Sam. Right in the middle of their complex calculation, they hit a massive, unexpected structural roadblock. They found a value for lambda, right? But when they plug it back into the equation, the numbers look incredibly messy. Just horrible, ugly fractions. Alex instantly panics, thinking they need to cross it all out, lose 10 minutes, and start completely over. This is exactly where we deploy the universal structural problem-solving matrix. Step 1, deconstruct. Break the given information into logical steps. Step 2, solve systematically. Step 3, evaluate and check for reasonableness. I step in as the master coach and I tell them, stop, don't erase a single thing. Look at step 3, evaluate. How can we check if this lambda is actually correct without completely redoing all of the algebra? Sam realizes it immediately. Oh, we can take our messy vector f, find the vector pf, and just do a really quick dot product with the direction vector of the line. If it equals 0, our messy fractions are completely correct. By applying that critical evaluate step, they anchor their argument. They perform the quick check, it equals exactly 0, and they confidently move forward, literally saving themselves 10 minutes of panicked recalculation.
And guys, this is exactly what the principal examiner means when they state in their reports, clear working out and proper presentation conventions secure the method marks. Using that deployed matrix, Alex and Sam rewrite their working out, loud, line by line, and I want you to model this in your exams. Alex says, okay, step 1, state the general position vector. Check. Step 2, find the vector connecting the point to the line. Check. Sam chimes in. Step 3. State the condition for perpendicularity explicitly. Write down that the dot product must be 0. Step 4. Substitute our expressions and solve for lambda. Check. And most importantly, they follow strict presentation conventions. They make absolutely sure they're using proper headings. They ensure their I, J, and K notation, or their column vectors, are cleanly written without mixing formats midway through because examiners hate that. They even annotate their steps, literally writing a tiny note on the side, since lines are perpendicular, dot product equals 0. This flawlessly engineered, top-tier response block leaves absolutely no room for an examiner to dock a method mark. It is bulletproof.
Welcome to Act 4. It is time for an interactive visual workshop. I want to test you under pressure.
I'm starting a 60-second timer challenge right now called the Visual Data Scan. I want you to imagine you are sitting in the exam hall. It's a high-stakes 8-mark question. Line 1 has a direction vector of 1, 3, -2. Line 2 has a direction vector of -2, -6, 4. The question asks, determine their geometric relationship. 50 seconds left on the clock. Now, the average student panics here and immediately sets up massive, complicated simultaneous equations for lambda and mu. 40 seconds. They are burning precious time. 30 seconds. Look at the data interpretation requirements on the screen. What should you actually look at first? 20 seconds. Focus strictly on those direction vectors. Line 1 is 1, 3, -2. Line 2 is -2, -6, 4. 10 seconds. Do you see the pattern yet? Time is up. Listen, if you spotted that the second vector is exactly -2 times the first vector, you win. They are scalar multiples of each other. That immediately means the lines are parallel. You just completely bypassed all those massive simultaneous equations, and you just saved yourself 6 whole minutes of exam time to use on a harder question. That is how you play the game.
All right, let's move to Challenge 2. Spot the examiner trap. I am displaying a deeply flawed medium-tier student paragraph analyzing 2 different vector lines. I want you to read this carefully with me. The student writes, I set up the simultaneous equations for the I and J components using parameters lambda and mu. I solved them and found that lambda equals 2 and mu equals -1. I then substituted these values into the K component equation. The left side gave 5 and the right side gave 8. Since 5 does not equal 8, the equations are inconsistent, therefore the lines do not intersect, so they are parallel. Okay, look closely. I want you to locate the exact line where poor logic and a total lack of structural precision completely drops the critical evaluation mark. Where exactly did this student fall apart? Think about it.
Let me bring out the digital highlighter and cite the exact principal examiner report warning for this scenario. Examiner alert, the classic trap in 3.7 vectors is using the wrong approach for the wrong context. Look at the text. The student did everything perfectly procedurally up to the very last word. They successfully proved the lines do not intersect, but here is the trap. In 3D vector geometry, lines that do not intersect are not automatically parallel. They could easily be skew lines. The student completely failed to check the initial direction vectors to see if they were scalar multiples first. Because they provided a generic, flawed logical leap that was not specific to the three-dimensional context, they lose the final, highest value evaluation mark. Your answers must always explicitly link to the given scenario and follow robust mathematical logic. Remember this rule. Not intersecting in 3D means they are skew unless you have already explicitly proven they are parallel.
We've made it to Act 5. It's time for the ultimate strategy recap.
Back in our study suite, Alex and Sam have completely realized that blending fast data inputs with a heavily structured argumentative thesis is the ultimate sweet spot for Cambridge math. We have decoded the problem, we solved it systematically, and we evaluated the examiner traps. To ensure you can replicate their exact success in your own exams, I am distilling this entire masterclass into 3 universal operational rules. Rule 1, the 3-step question scan. You must decode the question before your pen touches the paper. First, identify your position and direction vectors. Second, identify the command word. Is it calculate, or is it heavily analytical like show that? Third, visualize the 3D geometry in your head before writing a single number. Rule 2, the marks per minute formula. A standard Cambridge A-level math paper requires you to work at roughly 1.5 minutes per mark. If it is an 8-marked vector question, you have exactly 12 minutes. Do not burn 8 minutes doing pointless simultaneous equations if a 10-second direction vector check proves they are parallel. Protect your time. Rule 3, the post-writing compliance audit. This is absolutely critical. Before you move to the next question, audit your own work. Do you have proper headings? Are your column vectors properly formatted? Did you actually answer the specific contextual question they asked?
And finally, I have to reiterate the top 3 fatal examiner traps that you must proactively defend against on test day. Trap 1, using the wrong approach for the context. This is the skew versus parallel trap we just dissected. Don't fall for it. Trap 2, forgetting your format checks. Leaving your final answer as an incredibly messy string of mixed mathematical notations instead of a clean, clearly defined vector equation.
Trap 3. Generic, nonspecific answers. If the question asks for the position vector of an intersection point of two specific submarines in a real-world modeling question, and you just write x equals 4 at the bottom of the page, you haven't linked your point to the given scenario at all. You have to state it explicitly. The position vector of the submarine's intersection is, context is everything.
You now have the exact examiner's blueprint for 3.7 vectors. You know exactly how to structure your answers, how to build an analytical thesis, and exactly where those hidden marking traps lie. But remember, this is just one topic out of dozens. So I want to know, which Cambridge subject and level are you preparing to conquer next? Is it A-level physics? Maybe O-level chemistry? Drop a comment down below right now and tell me your exact syllabus. And make absolutely sure you are subscribed to Ace the Exams at the handle @AceTheExams. Smash that notification bell and join us for the next masterclass where we will continue to decode the examiner grids one topic at a time. Keep your reasoning logical, keep your working structured, and go secure those top-tier marks. I will see you in the next session.